Prevention of malfunctioning of relief valves. Relief valves must operate with high reliability under all conditions. However, several environmental and process-related factors can impair their performance, such as hydrate formation, corrosion, freezing, or fluid solidification. To maintain functional integrity and avoid unplanned releases or failure to relieve, appropriate design, material selection, and operational safeguards must be applied. 1. Protection against hydrates and freezing. During relief events, the Joule Thomson effect can cause rapid temperature drops, leading to hydrate or ice formation at the valve outlet. While high flow velocities during discharge typically prevent blockage during relief, small leaks across the valve seat can allow moisture to accumulate and freeze during normal conditions. To mitigate this, install heat tracing around the relief valve and associated piping. Ensure the heat tracing system is monitored and alarmed to detect loss of function. Consider chemical inhibition, e.g. methanol or glycol injection in hydrate-prone systems. Number 2, protection against corrosive and toxic fluids. Certain process fluids, e.g. sulfolane, hydrogen fluoride, hydrochloric acid, can aggressively corrode valve internals, leading to mechanical failure or leakage. Valves may not be fully leak-tight under all conditions, allowing trace corrosive vapors to escape into connected flare systems or the atmosphere. Mitigation strategies include selecting corrosion-resistant materials for the valve body and internals, installing a purge or flush system using clean, compatible fluid to prevent direct contact with corrosive service fluids, using a bursting disc upstream of the relief valve to act as a corrosion barrier and prevent vapor escape through the valve seat. 3. Protection against fluid solidification. Fluids with high pour points or waxy constituents may condense or solidify in relief valves or downstream piping. Even if valves are located in vapor spaces, entrained liquid, condensation, or spray entrainment during a relief event can carry liquid into the valve internals. If solidification occurs, the valve may become partially or fully blocked. Preventive measures include heat tracing and insulation of the valve, inlet, and outlet piping to maintain temperatures above the pour or crystallization point, flushing systems to displace and remove residual liquids after relief or during operation, use of a local knockout drum to separate entrained liquids before discharge into the flare or vent system. Relief valves operate under extreme conditions and in highly variable service environments. Anticipating and mitigating the most common failure mechanisms, freezing, corrosion, and solidification, is essential to ensure that these critical safety devices perform on demand without restriction or degradation. Proper material selection, heating systems, purge design, and procedural controls all contribute to sustaining their long-term reliability. Emergency depressurization systems. General principles. Relief valves are designed to protect against pressure excursions by releasing limited amounts of process fluid. However, they cannot effectively reduce pressure throughout an entire system or vessel. In high-risk scenarios, such as fire exposure or major leaks, emergency depressurization becomes essential to quickly reduce internal pressure and prevent rupture, escalation, or boiling liquid expanding vapor explosion, BLE. Emergency depressurization is typically initiated by operators or automatically in unmanned facilities. It must be possible to activate the system remotely, most commonly from the control room or a designated safe area. These systems are not used for routine shutdown or maintenance venting. They are designed solely for rapid pressure reduction during defined emergency events and must be treated as part of the facility's critical safety layer. Determining the need for depressurization. Depressurization is required where the risk of fire-induced or leak-related failure is significant and could lead to hazardous consequences. The assessment focuses on fire exposure. If equipment or piping could be exposed to flames, reducing pressure mitigates loss of mechanical strength due to elevated temperatures. Inventory hazards, systems containing significant volumes of flammable or volatile liquids, e.g. butane or lighter hydrocarbons, must be depressurized to prevent BLE. Personnel safety and equipment proximity. Systems near occupied buildings or high-consequence areas are prioritized for depressurization. Depressurization is mandatory for high-pressure systems in hydroprocessing units, e.g., hydrotreaters, hydrocrackers, desulfurizers, all manned offshore installations with high-pressure equipment, systems containing at least 4 millicuries of volatile hydrocarbons under normal conditions. For liquefied petroleum gas, LPG bulk storage, emergency depressurization is typically not required due to the low likelihood of liquid pool fires and the use of dedicated firewater sprinkler systems as the primary safeguard. Emergency depressurization valves must be dedicated for this function and not shared with relief valve service. Their design, sizing, and actuation must be aligned with the broader process safety and fire protection strategies of the facility. Attached sectioning of process systems for depressurization. To manage emergency depressurization effectively, especially in large, complex facilities, process systems should be divided into discrete fire zones or depressurization segments. This strategy helps to control the peak flow rate into the flare or vent system and limits the impact of depressurization on the facility's utility systems and flare capacity. Key considerations in sectionalizing a facility include zoning based on fire exposure. The plant should be subdivided into logical fire zones, typically sized around firewater drainage layouts or areas of concentrated hydrocarbon inventory. Each zone should be isolatable via emergency shutdown (ESD) valves. Independent depressurization. Each section must have its own depressurization valve, S, allowing zones to be relieved independently and sequentially, rather than all at once. Sequential depressurization. After initiating depressurization in the first zone, others may follow in sequence, only after the initial flare load has decayed sufficiently to avoid exceeding design limits. This stepwise approach smooths out peak demands on flare and utility systems. It is critical to ensure that the control system and procedures prevent common mode failure, such as a loss of power or instrument air, from triggering all depressurization valves simultaneously. Utilities, instrument air, power for each zone are separately sourced or protected to avoid simultaneous loss across multiple zones. This zoning strategy may not be feasible in some cases, particularly on integrated offshore platforms where space and layout constraints limit the ability to physically separate flare segments. In such instances, the entire platform may depressurize as a single system, and the flare must be sized accordingly. By implementing fire zone segmentation and sequence depressurization logic, facilities can maintain flare system integrity, reduce mechanical shock, and improve overall emergency response effectiveness. Depressurization design considerations. Effective emergency depressurization design must ensure that equipment integrity is preserved during high-stress events such as fire exposure or significant leaks. Depressurization systems must reliably and rapidly reduce pressure within safe limits, taking into account thermal effects, material limitations, and flare system capacity. Key elements of depressurization design include valve requirements. Depressurization valves must be dedicated devices, separate from relief valves. They should be remotely operable, typically from the control room or remote safe location. In unattended or automated operations, the valves must be automatically actuated by triggers such as fire or gas detection. For critical systems, e.g. containing toxic or high-energy fluids, depressurization may also serve as a means to reduce release duration during leaks. Valve sizing objectives. The system must be capable of reducing pressure to 50% of the equipment's design pressure within 15 minutes during fire exposure. This 15-minute window does not imply depressurization ends after that period. Rather, it represents the required rate for initial pressure reduction. In some systems, especially those with slow warm-up behavior and normal operating pressure well below design, sizing may instead ensure that pressure does not reach 50% of design pressure within 30 minutes. For rotating equipment, faster depressurization may be needed to avoid seal oil system failure. The required time should be confirmed with the equipment vendor. Key parameters for depressurization calculations. Depressurization models must account for flash vaporization of liquid due to pressure drop, changes in vapor density and volume as pressure decreases and temperature rises, continuous heat input from external fire throughout the depressurization period, Initial pressure assumption should be the higher of the set pressure of the relief valve, the pressure estimated after 15 minutes of fire exposure. System boundaries and inventories include all vessels, piping, and equipment located within the fire zone. Account for any equipment outside the fire area that remains connected and exposed to pressure from within the zone. Consider both vapor and liquid inventory, especially where flashing and vapor expansion are expected. For columns, include bottom and draw-off tray volumes, tray liquid holdup based on normal pressure drop. For heat exchangers, assume the tube bundle occupies 1/3 of the shell volume. Assumptions regarding fire protection. Active fire protection systems, e.g. deluge, are standard, but their operation cannot be guaranteed, so they must not be credited in sizing calculations. Passive protection, e.g. fireproof insulation, may be considered if properly verified. Depressurization valve sizing and placement must be based on realistic, conservative assumptions to ensure system safety during the most hazardous conditions, especially fire. The design must also align with flare system capacity, avoiding overloading while maintaining sufficient pressure relief speed to protect structural integrity. Evaluation of depressurization rate. The depressurization rate must be sufficient to ensure that internal pressures in vessels and piping do not exceed allowable stress limits, especially during fire exposure. Calculations should demonstrate that the system can achieve the required pressure reduction within defined timeframes, without causing equipment damage or overloading the flare system. Key practices include use recognized methods to evaluate the pressure decay curve and associated vapor flow rates. Application of dynamic simulation tools, e.g. process modeling software, is highly recommended to account for inventory behavior, thermodynamics, and phase changes during depressurization. The calculated initial vapor flow rate from depressuring valves is typically higher than the final flow at the flare tip due to line packing, where vapor fills available piping volume, increasing transient flow to the flare system. This effect can be credited only if a validated dynamic model demonstrates safe performance. Otherwise, it must be neglected in flare sizing. Low temperature evaluation. Emergency depressurization leads to rapid expansion and vaporization of fluids, often resulting in significant temperature drops. These low temperatures can cause materials to become brittle, potentially compromising the structural integrity of equipment and piping. Design considerations include evaluate minimum metal temperatures expected upstream and downstream of the depressurization valves during full venting. Select materials of construction that remain ductile at the lowest anticipated temperatures, particularly for equipment that may be repressurized soon after depressurization. If rapid repressurization is possible, consider the combined effects of high pressure and low temperature when selecting materials. Material selection must comply with relevant fracture toughness criteria and applicable piping and pressure vessel design standards. Depressurization device location. The location of depressurization valves follows the same general principles as relief valves, with a focus on minimizing pressure drop, avoiding obstructions, and ensuring effective isolation of each depressurization zone. Best practices include install depressurization valves as close as possible to the equipment or piping section being protected. Valves may discharge into the same flare or vent system as associated relief valves, provided the system is designed to accommodate the combined flow. Be mindful of the position of check valves or other one-way devices, ensuring that downstream equipment is not unintentionally isolated from depressurization paths. Locate valves and piping to allow for routine testing and maintenance with appropriate safe access. Use piping layouts that prevent liquid accumulation, avoid low points, and allow for free draining to reduce risks of hydrate or ice formation. Careful placement of depressurization valves ensures that they function effectively during emergencies while remaining accessible and maintainable throughout the system's life cycle. Flare and vent systems, general purpose and design considerations. Flare and vent systems provide a safe disposal path for relief and depressurization flows, whether during normal upsets, emergency conditions, or controlled process events. These systems are critical to prevent uncontrolled releases of flammable, toxic, or high-pressure materials. Key design objectives include ensuring safe, continuous disposal of relieved gases under all operating scenarios, preventing exposure of personnel and equipment to toxic or flammable vapors, limiting environmental impact, noise, and thermal radiation, maintaining system integrity during simultaneous high-flow events from multiple sources. The upstream and downstream piping, headers, and flare tips must be designed holistically, considering all anticipated load cases and worst-case combinations of relief and depressuring flows. Design of piping upstream of a relief device. Relief valve performance is heavily influenced by the characteristics of the upstream piping. Inadequate design can lead to excessive pressure drop, valve instability, or destructive valve chatter. Key requirements. Use full-bore piping and fittings between the pressure vessel and the relief valve to match or exceed the valve inlet area. Avoid flow restrictions and pockets that can accumulate liquids or solids. Limit the pressure drop in inlet piping to 3% or less of the relief valve set pressure to prevent valve instability. For liquid service, additional care is required due to the incompressible nature of liquids. Pressure drop during flow acceleration can quickly exceed tolerances. Relief valves handling cold streams may require uninsulated inlet piping to prevent valve icing, or alternately, heat tracing to prevent blockages. For hot streams, a short length of uninsulated piping may be used to reduce valve material temperature, but designers must account for risks of condensation, fouling, or wax formation. Where multiple valves share a common connection, the shared pipe must have a cross-sectional area equal to the sum of the valve inlets. Pressure drop limits still apply for total combined flow. Selection of gas disposal systems. The method of gas disposal, whether by venting or flaring, depends on environmental, safety, and regulatory factors. Key disposal scenarios include relief events, emergency depressuring, and planned operational venting. Venting versus flaring. Venting may be acceptable if it occurs only during emergency scenarios. Vapors are lighter than air, and adequate dispersion is assured. The stream contains no liquids, no risk of condensation, and no flammable or toxic concentrations at ground level. Ignition risk is negligible due to equipment spacing and layout. No combustion products, e.g. soot or unburned hydrocarbons, will be released into the environment. If any of these conditions are not met, flaring is preferred or mandatory. Common vent systems. A shared vent header may be used if vapors are chemically compatible and will not react or condense into harmful substances. The system includes adequate liquid knockout capacity. The design avoids blockages or backflow risks during high-volume events. Flare system segregation and recovery. In large or complex facilities, segregated flare systems may be used to manage different flow types, reduce costs, or improve combustion performance. Common segregation strategies include high and low pressure separation, especially to accommodate different back pressure tolerances or tip types. Isolation of corrosive or toxic gases, e.g. H2S-rich streams, to avoid widespread contamination and corrosion. Separation of wet and dry streams to prevent hydrate formation or freezing. Flare gas recovery systems may also be implemented to reuse vented hydrocarbons, minimize emissions, and reduce flare load. Discharge back to process or storage. Where feasible, some relief streams may be safely routed to lower pressure process equipment or storage vessels instead of the flare. This is viable only if the discharge will not cause overpressure or overfilling of the receiving system. The flow does not conflict with normal operations or create hazardous conditions. No reverse flow or relief valve leakage occurs due to low back pressure in the receiving system. Back pressure assumptions must be conservative, and interactions with other relief devices must be validated. Disposal of thermal expansion relief valve, TERV. TERV discharges should ideally return to the process system, a dedicated closed relief header, a safe storage or handling system. If no closed path is viable, and if permitted by local regulations, TERVs may discharge into open drainage systems. However, this is restricted to non-toxic, environmentally benign fluids. For toxic or hazardous fluids, closed containment is mandatory. Disposal of hydrogen sulfide-rich gases. H2S-rich gases require special handling due to corrosion, toxicity, and potential for widespread contamination. Disposal options include dedicated sour flare systems with corrosion-resistant materials and flame-arresting tips, injection below water seals of existing flares, only if H2S content is low and does not pose material compatibility issues. Separate headers and Schratt flare tips designed for H2S service are preferred where concentrations are high. In all cases, the objective is to avoid mixing H2S with general hydrocarbon relief streams, which would spread contamination and corrosion risk throughout the flare system. Discharge of oxygen-containing streams. Any gas stream containing air or oxygen must be kept isolated from combustible or sour gases. Mixing oxygen and hydrocarbons in the same flare header presents a severe risk of explosion due to flammable mixtures, internal oxidation and deposit formation, corrosion from acidic or sulfur-containing products. Such streams must be routed to dedicated flare or vent systems, or inerted prior to disposal. By designing flare and vent systems with these principles, process facilities can maintain safe, reliable disposal of overpressure events while meeting stringent environmental and operational standards.